This is a follow-up to a video I made recently about the cassette interface in this Altair 8800 computer. And in that video, we made a drop-in equivalent for the original cassette interface, but we did it using hardware that was a bit more readily available. Now, if you haven't watched that video yet, I would really recommend watching that first. To help you find it, I've put a link to that video in the description of this video. Now, the interface that we made in that video was a two-board set, just like the original Altair interface was a two-board set. One of those boards is a fairly standard serial interface board like you see here. This plugs into the bus, and this is what the software actually talks to in order to transfer data. The other board is a modem board. It takes the serial data out of this board and converts it into a pair of tones that then get written to tape, and then of course tones coming off the tape get converted back into serial data that can come into a UART and then be read by the software. Now, any serial interface board that you choose to do this project, it's going to have to look exactly the same as the serial board that was used in the original Altair Cassette Interface. That's an 88 SIO. The board you're looking at here is the board we used in that last video. It's a solid-state music IO4 board. And this board was one, it was not hard to configure to look exactly like the cassette interface serial board. However, there are not a lot of boards that can do that. There's some restrictions. Specifically, it's going to have to use the same UART that was used on that SIO board of the cassette interface. And we'll touch again on that in just a minute. So in that last video, I created a link to a file I made that was a list of serial boards from back in the day that I thought you might be able to use in order to create your own cassette interface. Boards in addition to the solid-state music IO4 board that we demonstrated in the video. Since then, I've been able to actually test several of those boards, prove that they work. I've found some that were very easy, some that required a couple of minor mods, and then others that I could actually just write off the list. They're not going to work. And so that's what we're going to do in this video. We're going to take a look at some of these additional boards I've found that can be used as the serial interface board in a drop-in equivalent for the Altair Cassette Interface. The first board we're going to look at is a board that wasn't even in the list of potential boards that I created after that last video. In fact, I only learned about this board about a week ago, but it turns out that this board is really easy to make work as the serial interface portion of the Altair Cassette Interface. The reason for that is because it is actually the same thing as the blue IO4 board, solid-state music, that we used in that video. So it turns out that the company called ICC, which stands for International Cybernetics Corporation, bought a bunch of IO4 boards back in the late 70s to put into their process control machines. These were S100 computers that they sold to run factories, to run CNC machines, that kind of thing. And they sold enough of them that eventually they got solid-state music just to private label the IO4 board for them and sell it to them. So this is really just an IO4 board, but it says ICC on it. Doesn't have any information about solid-state music on it at all. And they continue to buy these for a number of years. In 1985, Gould, you can see that there as a Gould part number, bought ICC. And they were still buying these in 1985. And that's a pretty good long run on boards that were getting pretty antiquated by 1985 otherwise, at least in the personal computer market because of the PC being developed. But anyway, since this is an IO4 board essentially, this is another great candidate for building an Altair Cassette Interface. Now, another good thing about this board is unlike the solid-state music board that shows up just every now and then on eBay, there's a bunch of these available for sale on eBay, at least here in the near term. And so this is a good chance to get one of these for yourself. All right, so this is a candidate. I'll add this to the list, and we'll move on to the next board. The next board we're going to look at is this Altair 88 SIO board. Of course, this is the same board that's used in the cassette interface itself, and in that last video I said this would not be a good candidate because it's going to be rare just like the cassette interface itself is rare. However, I didn't tell you the entire story. There's actually three versions of this board. There's the 88 SIO-A, SIO-B, and the SIO-C. These boards are all identical other than the electrical interface that is right here in this section of the board. The SIO-A, which is what you see here, drives this interface, the serial data, with RS-232 levels. The SIO-B drives that interface area with TTL levels. And it's the SIO-B that's actually used with the cassette interface. And finally, the SIO-C it has current loop interfacing on the serial data that allows it to work with the teletype. All right, so the SAOB's production was used mainly for the cassette interface. So that's why there's not a lot of those free, independent of an interface board set to use. However, the SIO A and C, frankly, those were the only serial boards available for the Altair for almost a year. And so there are more of these that show up. I mean, it's still not an extremely common board, but they do show up from time to time, and so you might get one. So what we're going to show you today is how one of these would be used to make your own cassette interface using the exact same setup we used in that previous video. Now the board you're looking at here is the SIO-A. So this is an RS-232 interface over here on this side. And this will work good with our setup because of course we expect all of our interface boards to have an RS-232 interface to hook to the modem. So what would it take to get this board working? Well, again, the criteria is that the I/O ports for the UART need to be at I/O addresses 6 and 7, and we set that right here with these hardwired soldered jumpers. And so we've set that to I/O address 6, which puts the status port at 6 and the data port at 7 for us. That part's already correct. The next thing we need to do is make sure that the receive data available flag is on bit 0. And the transmit ready flag is on bit 7 of the status word, and those bits use negative logic, meaning 0 is true. Now this is the SIO board, the same as used in the cassette interface, so you would think I don't have to worry about that. However, you do, and the reason is because the very first versions of this board did not work that way. So if you want a board that has that configuration, it either needs to be a Rev 1 board, or it needs to be the Rev 0 board with the Rev 1 updates. Now, it sounds like you might run into quite a few Rev Zeros without that update, but in reality, pretty much any board you find is going to have the update because they ended up actually calling it errata, meaning it needed to be fixed as opposed to an update. And the reason for this is because the very first versions of the SIO board used a very odd protocol with the serial data. It actually required a handshake line between each character in each direction, both directions. Much like a serial port where you have a strobe when the data comes in and then another strobe for data going out. And so you probably have never seen a serial port that works that way. I haven't either. So it wasn't long until they quickly changed all these boards for the most part to use the more common serial interface. And that's in this case where we have data ready on bit 0, transmit ready on bit 7 with negative logic. So this board has that already because it is a Rev 1 board. The next thing we need to do is set it for 8 bits, no parity 1 stop bit. That's what these jumpers all here do. These tie these pins on the UART to 1 or 0, 5 volts or ground to choose those various options. And that'll be common on all these boards that we look at that use this UART. And finally, we need to set the baud rate to 300 baud. And that's done with all these jumpers down here. There's a bunch of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It takes 12 jumpers to set the baud rate, and they're all solder jumpers. So not an extremely convenient board for changing the baud rate. But once you have this set up to run at 300, you'll probably never change it again if you're making this part of your cassette interface. All right, so that does the configuration. At that point, data comes in and out of this connector. It's labeled right on the board. We have a transmit and a receive and a signal ground. And of course, that's all we need to communicate with a cassette interface. This board also has 5 volts on this pin right here. And if you recall, I picked up that 5 volts on the IO4 board and put it on pin 18 of the DB25. That made it very easy to power that cassette interface without having to run separate power wire to that. So in all these demonstrations, I'm going to get 5 volts hooked to that right wire in order to get it onto pin 18 on the DB9. All right, let me step back just a little bit here to make room to show you this. This is the harness I made to connect to the board. I didn't have the full width one, but I have it marked so I know where to put it on. And then the DB25 will go in the back. So let me go ahead and do a video cut and we'll take a look at this inside the computer ready to go. If we look inside the computer, we can see our 88 SIO board installed right here. We have the connector attached now that's going to run to the DB25 in the rear panel. And then as before, we're using the cassette interface board from the Altair clone as our modem. This board is still readily available. You can go to the altairclone.com website and order one if you want. It converts audio data to and from these two jacks into RS-232 data that also goes to this rear connector right next to the one from our SIO board. And then to hook the modem to the serial board, I just have a jumper cable going between those two DB25 connectors. Now our modem is connected to the serial interface board. Now both of those connectors are wired as DCE, so I have to swap pins 2 and 3 between them, and that's what this little twist does right here. But for several reasons, I want to leave those both as DCE, just like I mentioned in that previous video. All right, so that's all it would take to get an 88 SIO version A, which is RS-232 already, up and running inside your Altair as a completely equivalent drop-in replacement for the Altair Cassette Interface. The next board we're going to look at is this 2718A made by California Computer Systems. Now there was a 2718 as well without the A on the end, but that's a substantially different board, and so what I talk about today doesn't apply to that, just to this 2718A. And this board is more common anyway, and most likely what you would find if you were out shopping for one. All right, this board has 2 serial ports on it, 2 parallel ports, and some EEPROM space on it. The 2 UARTs are here and here. You can see they're 2 different UARTs. This 40-pin one is the one that we're going to use as our cassette interface equivalent. The other UART is an 8251, which actually can do synchronous communication as well. Now there's no native support in any Altair software for that UART. Doesn't mean you couldn't write something if you wanted to use that serial port. The EEPROM on here can come in kind of handy if you don't have other EEPROM in your system. For example, you could put a nice monitor on there, and you still have plenty of room to put all of Altair's ROMs on there. Those are each only 256 bytes because it was for a small 1702A EEPROM. So you could put the turnkey monitor, you could put the disk bootloader, and of course you'd want the multi-bootloader. That's the ROM that allows you to boot from paper tape or cassette without having to toggle in a bootstrap loader on the front panel. So I've got an EEPROM in here, and we're actually going to go ahead and use that in the demo today. All right, to get this board working like we need for cassette interface, the first thing we need to do is have the UART that we're going to use show up at IO address 6 and 7. Now on this board, both serial ports are set with a single set of jumpers, these right here. And what those do is set a group of 4 registers at address 0, 4, 8, etc. So I have this set right now to put the 2 UARTs at address 4. And now we need to make sure that our UART is at 6 and 7 and the other UART is at 4 and 5. That's done with this last jumper you see right here. So presently this is set to put the UART we're going to use at IO address 6 and 7. The next thing we have to have is that the status register is first at 6 and the data register is second at 7, as opposed to the other way around. And that's done with this jumper or the next jumper over. So that has our status register at 6 and the data register at 7. Next, we need the status register bits to map to where we need them. We need receive data available excuse me, on bit 0, the least significant bit, and we need transmit data ready on bit 7, the most significant bit. And like on the IO4 board, we do that with this header right here. This maps bit 0 and this maps bit 7 to receive data available and transmit data ready. Those are now in the right position, and now we need the correct polarity. And we need negative polarity, meaning that it's true when it goes to 0. And like the solid-state music board, we do that by choosing the right buffer that buffers this status register onto the bus. With a non-inverting buffer, like an LS244, we get positive true logic. With an inverting buffer, I put in an LS240, we get inverted data or negative logic like we need. So at that point, all those conditions are satisfied. We need to look just like the original SIO board as far as software is concerned. All right, now we need 8 bits, no parity, 1 stop bit. That's done with these jumpers right here, which simply set the levels over here on pins on the UART. So that gives us our 8 and 1. We need 300 baud. That's done with the upper 4 jumpers here. So that's pretty easy to set to. And at that point, this board is ready to go as far as getting our serial interface working. And to make it look just like the cassette interface. Now, the serial data comes through these 2 ports up here. This second port is the one that's used for the cassette interface UART that we'll be using. That's a 26-pin standard IDC header, and that allows us to use just a simple ribbon cable like this to go to a DB25. Our socket plugs in there, and this goes back to the rear panel. The way this is wired, that straight through ribbon cable comes out as DCE, which again, that's what we need. That's how we expect our serial ports to be wired in the back. So that works out well. Now I do want to have 5 volts on pin 18 of the DB25, and as you would expect, this board does not happen to do that for us because that's not like a standard of any sort. So if you look real carefully, you can see I put a little jumper wire on here. That's this little blue wire right there. I don't know if you can see it. That's going from 5 volts, and it's putting it on an IDC pin that'll end up on the DB25 pin 18. So there's my 5 volts on there. So at that point, the serial board is ready to go to look just like a cassette interface. Now, as far as the EEPROM goes, we set the address with the first 5 of these jumpers. I have it set at F800. So this EEPROM will run from F800 through FFFF, the top of RAM, the top of memory space. And at F800, I have myself a monitor, and then at FD100, I have the turnkey monitor. At FE100, I have the multi-boot loader, and at FF100, I have Altair's disk boot loader. Those are all the standard addresses for those. Now, one kind of neat thing about this EEPROM is that it only takes up as much address space as you have programmed. And it does that by whenever the data is an FF, whenever it's returning all ones, which would be like if nothing was there, or an empty spot in an EEPROM, it does not enable the bus drivers at all. But it still looks like an FF to the CPU because there are pull-ups on the data pins on the CPU board in an Altair and an MSI and several other early CPU boards. Or at least if you have termination resistors, or active termination even on the bus, then an open, nobody driving the circuit will also look like ones. And frankly, even if you didn't do any of that, it's probably going to look like ones anyway, just because that's the way TTL works. So anyway, if you have no EEPROM in here at all, everything will return FF, so this board will never drive the bus for whatever address you have selected. If you only had one EEPROM, like Altair size at FF00, just 256 bytes, everything below that would return FF. None of that would actually activate on the bus either. So you don't actually have to lose much address space if you're not using the entire EEPROM. Just kind of a cool trick. I know of one RAM board that works that way as well. All right, so this board is ready to go. Let's go ahead and hook this up inside the computer and load BASIC and see how it works. All right, I've got the 2718 installed down here at the very end to make sure this ribbon cable could reach easily. I've moved my 2SIO, well, 2SIO JP in this case, in a couple positions, and I have its ribbon cable going to the back for the console. There you can see the ribbon cable for the 2718 going to the back, and then of course I have the jumper in the back to hook that 2718 to the modem board. All right, let's go ahead and turn this on. Give it a reset. Examine FE00, that's the multi-boot loader. Tell it once BASIC's up that you're going to run from a 2SIO. Tell it with a 3 here that we're going to run from cassette. I'm going to release the cassette to start playing and hit run. And off it goes. At this point, it's going to load BASIC. This will take about 4.5 minutes. And I'll come back when that's about done and we'll just quickly demonstrate that it's up and running. All right, this should be nearing the end of the load soon, and when it does, we will see this light pattern here on the front panel change, and we should see a prompt come up over there over on the terminal. There we go, there's the pattern change, and there we can see our memory size prompt. Let me go ahead and stop the tape. And we can see BASIC's up and running. All right, so that board works quite nicely. I'm not going to go any more demos. It's all stuff you've seen before. Now, there is one thing to point out about this board, and that is that the silk screen on the board for all of the address labels is basically wrong. On my board, it shows 0 as being up towards the top of the board and 1 as being down. In reality, it's the exact opposite of that. If you want 1, the jumper should be towards the top of the board. If you want 0, it should be towards the bottom of the board. In the manual that I found for this board, it actually has one set of jumpers one way, the other set of jumpers the other way. And then in a silk screen on a later rev of the same board, it's the opposite of the manual. But all 3 of those appear to be wrong from what I can tell, at least for the version of the board I have. And my guess is that they're all the same as mine, where 1 is up, 0 is down. Now, if you do get this board, All I would say is don't trust the silkscreen, don't trust the manual. Make sure you take a look at that board and see how it's actually wired. My guess is it's going to be like mine, where a 1 is up, a 0 is down, and you'll have to look at the schematic to see how that select logic works with exclusive OR gates to know for sure. If you have any questions, you can certainly reach out to me, but this board works well as a cassette interface board. The last board we're going to look at is this Interfacer 1 made by CompuPro or Godbout. This has 2 of the UARTs on it that we need. And what's interesting about this board is rather than just group those into 4 consecutive addresses, they provide separate address switches for each of the 2 serial ports. And this is unlike the other boards with 2 ports we've looked at, so we can do something with this we can't do with those others. And I'm going to use one of these serial ports to be our cassette, of course. I'm going to use this one, which is port B. The first port, I'm going to use that to look like an 88.2 SIO serial board of Altair's, because the 88.2 SIO was by far the most common console port that was used. And I can do that because the 2 SIO was up at 10 hex, which is 16 decimal. Cassettes down at 6, those are not consecutive. However, since we can separately address them, I can do that. And at the end of this video, the end of this section, I'll show you how we make that serial port work for the console. But going on, we're going to first just look at how do we make this work as the cassette like we have for the other boards. First thing we need is addresses at IO addresses at 6 and 7. That's done on this lower set of dip switches, which sets the starting address for UART B at 6. And then, of course, the next register to be 7. And then the next thing we want is we want status at 6, data at 7, as opposed to the other way around. That's done with this ABC jumper here. We've connected A to B. That gives us status first and data second. In the B to C position, you get the opposite. And B to C is a default on this board. There is a trace in there to begin with. So if you really want to use this ABC jumper, you have to cut that trace first, and then you can wire either way you want, or install a 3-pin header and use a jumper. All right, the next thing we need is to have receive data available on bit 0, and we need transmit data ready on bit 7. Now, you'd probably think that these jumpers are how we're going to do that, like we did with other boards, but those are for another purpose altogether. In the end, this board does not have a way to reconfigure the status register. So the only way we can do it with this board is to cut some traces and install some jumper wires. So that makes this a little less convenient than some of the other boards, but it's really not that hard to do. You see a few blue wires. Ignore most of those, except for there's 2 over here that are the ones that routed bit 7 or transmit data to bit 7 and receive data to bit 0. I had to cut a trace over here to free up one of those pins. And rather than cut a second trace to free the other pin, I was actually able to just lift a signal on a chip right here that goes to the pin we needed to use. That signal is not used for anything else, and so I can just lift the pin out of the socket, and that saves having to cut that second trace. At that point, I have received data on bit 0 and transmit data flag on bit 7 like we need. The next thing we need to do is invert that data so that we have negative true logic. So as before, we're going to go ahead and replace a positive non-inverting buffer with an inverting buffer of the status register, just like we did for the other boards. Now you notice this is a 20-pin socket, and I put a 16-pin chip in here. The buffers they used were not the typical 8-bit buffers of the 74 LS244 and the LS240. Instead, they used an 84 series buffer. Also, a 74 LS795 is an equivalent as well. Both of these are fairly rare. They have a totally different pinout than the LS244, which was kind of a standard. What these chips were was like an upgrade path from the very popular 6 element buffers, the 74, 367, and 368. It has the exact same pinout for the first 3 buffers on this side and the last 3 buffers on that side as the 74 LS367 or 8. Now those are very common chips. I happen to have a 368, which is the inverting one in stock in my office, and all we really need is 6 of those buffers in order to fill the status register with the bits we actually need to drive. So I actually put a 368 in here. The first 3 are the same, the last 3 are the same. That covers the bits we're going to use. This upper pin in the corner, pin 16 or 20, that is VCC. The only thing we need to hook up still is pin 8 there for ground. Pin 8 is driven by this jumper ABC here. So I just connected that jumper to ground, and at that point pin 8 is grounded just like we need. So this works just fine. Now someday if I place a minimum order or exceed a minimum order, I'll probably add one of these chips in so I have the right looking chip in there, but this satisfies the purpose and gives us our inverted data. All right, the next thing we need to do is have 8 bits, no parity, 1 stop bit. That's what these jumpers actually do. And so that's the configuration for 8N1. I've done the exact same thing over here for port A, so we'll run the console port at 8N1 when we get around to doing that. Now what's interesting about this is those jumpers don't just tie to +5 or ground. Instead, they connect to these 4-bit flip-flops to get those 5-volt or ground signals. And at reset and at power on, those go to a defined state, so we always know what these jumpers mean after a reset or power on. However, those flip-flops can be written with an out instruction, and the out address is the very same address as the status register that we read. And so if software accidentally or software we don't know about writes to that address, it would end up screwing up our cassette interface because it could easily change the word size, parity, etc. So we need to disable writes to these flip-flops. And so I did that by lifting a pin out of a socket to disable that down here on this chip. One pin is lifted to prevent writes to the port 1. One pin is lifted to prevent writes to the second port on that. So that way they always behave exactly like we expected with those wired jumpers. All right, the last thing we need to do is get the baud rates right. So the top 4 switches on that set port A, the bottom 4 set port B. So of course I have port B set for 300 baud like we need for cassette. All right, data comes in and out of these 2 connectors up here. These are 26-pin IDC connectors like we saw previously. This allows us just to use a standard ribbon cable like you see here. It makes it very easy to wire to the rear panel. The data for the cassette comes out of this one right here, and this jumper allows us to wire it as DCE or DTE. And so the way I have these both wires to make them look like DCE, which of course that's how the cassette is defined and the way I have it configured. And of course if you're going to hook to a terminal, you want your computer to be DCE. All right, so at that point, this does everything we need to hook to a cassette. Now, as before, I'm going to want to add 5 volts onto pin 18 of the DB25. And that's this blue wire you see right here. That's going up to the IDC connector, hooking to 5 volts that's on the board. With that in place, I have the 5 volts to drive the modem. Excuse me. All right, now for the console serial port, that looks like a 6850 UART. That has received data on bit 0. The transmit flag is on bit 1. And it's not inverted, it's positive logic. But again, since there's no way to change how those bits are assigned, we're going to have to cut some traces and add some jumpers. So there's 2 parallel traces here that connect those 2 signals. I got those cut, and then on the back of the board, I have 2 blue wires that basically just swap those 2 signals because the interfacer had transmit on bit 0, receive on bit 1, and I needed them the other way around. All right, and then of course it's positive true logic instead of negative. I'm sorry, excuse me. And so I don't have to worry about changing out buffers. I just leave the buffer that's in there because it's already a non-inverting buffer. And at that point, our serial port for the console is good to go as well. So we'll set this up and take a look at it. And we'll not have to use a 2SIO board because this board will serve as our console port and as our cassette port. All right, looking inside the computer, you can see the interfacer board right here. Serial port 1 is going to the back where it's going to our console over to this terminal. And then serial port 2, that is our cassette. That's going down into the back just like before to connect to the modem through the jumper in the back. All right, now I've already booted up BASIC and have it up and running. Let's just give a quick demo here, just to show that we have a console port and a cassette port. So as you can see, I've been doing some things, and I can print 2+2. But let's go ahead and load off the tape. We'll load the primed program. Let me release the tape and hit return here. So our console is working off that first serial port. I'm about to use the cassette port. Hopefully this will load without any issue here. This is a short program. I've demonstrated it before. Shouldn't take long. Hopefully it's about done. There we go. And there's the prime number benchmark program loaded off a cassette. All right, so we have got a console serial port here using the 2 SIO equivalent that we made here on the interfacer board. We have the cassette interface on that same board, so kind of 2 for 1, that's nice. And we've demonstrated several other boards in addition to the solid state music that we can use to make a drop-in equivalent of the Altair Cassette Interface. Now I know there's at least one other board that's going to work quite nicely, and that's a board by ECT, or Electronic Control Technology, I believe it is. It's their R2IO or R2IO board. It's actually the easiest of all these boards. By default, it's configured just like an 88 SIO Rev 1 board, but instead of having to do all those solder jumpers like you do on the actual Altair SIO, it's just got some dip switches. So it makes it really easy to do this, but I've yet to be able to find one of those. But hopefully I will, and I can prove it's as easy as I think it is. Meanwhile, I have updated the file that contains the boards that work and removed the boards that don't work. I put information about how to jumper them, at least enough to get you started. And so if you want to see that updated file, the link is in the description of this video. All right, well, that does it for this video, and I don't know if there's any more to beat to death on this cassette or not, but it's been a fun journey for me, and I've learned a lot.